Okay, welcome back. We're going to carry on with our project, and we're going to look at some basic instructions that are used quite often. So we've already programmed a single run with a direct coil. We've used some bits, some direct bits as opposed to reverse bits. If you're not sure what the contact is or how to explain it, if you move the mouse to that contact, it will tell you what its proper term is. In this case, if we wanted to use the normally closed, we would call that a reverse contact. Examine if open. If I go to the first one, it's a direct contact. Examine if closed. Now, output, here, direct coil, output energized. A reverse coil, output de-energized. This is a set coil. In other words, we're going to make the run true to turn it on. And the only thing that will turn it off is a reset coil. So you have to have those in a pair. They both work together. Then we have these two, output pulse rising and output pulse falling. These rising edge and falling edge coils have a particular function, which we'll look at when we want an action to take place and be true for a single scan. But what I want to do now is I want to get into one of the biggest instructions sets that we use, which are timers and counters. So we're going to look at, I'm going to first of all create a new run. So this is my new run. It will default to the next position that's available. If I wanted to put a run before it, the simplest way is to that. And you see how the plus sign now is above the first run. So now the first one has become the second one. If I don't like that, I think I can just press Control Z and undo what I just done. There is a box above each run. And one of the things as a PLC programmer, you know what you did. The next person may have difficulty following it, especially when you get into tags or aliases or addresses or variables with cryptic names like system bits. The next person is going to look at that and go, okay, why does he have system bits? That makes no sense to me. So you can simply type in a comment above it, click the 5-bar, this run, and then I'll turn on and internal bit of system underscore bit 0 when the cycle start is pressed and the automatic push button is on. Automatic, I'm going to call it a selector switch. And then put bracket PV, because it can be a maintained push button. This way you know that, oh, okay, this one going to be on itself. And the cycle stop is not pressed. The coin will seal in via its own sealing contact. So the next person coming up, I know the type font is very small, there's ways that we can change out, but for now, the important thing to remember is you are not done programming until you put the comments. There is nothing more frustrating than to walk up to a machine, you're getting paid a lot of money, and people who have hired you to do the work, they are losing money because the machine is not running. and you have to reverse engineer every single one because the last person to program it didn't write any comments. A long time ago, 30 years ago, you didn't have the luxury of putting any commentary. So this very same one, just to give you an idea, I'm just going to do exactly the same one as it would have appeared 30 years ago. That's it. That's all you would have seen on the screen. There would have been these, and then they would have had cryptic addresses which only related to memory locations. There was no aliases involved. So I'm going to really go completely old school. So I'm going to just leave how to do it. So you knew that was some sort of an output. You knew that was some sort of an input. And then they used to have 500, and that told you was something internal. It was completely cryptic. You had fan-fold paper printouts that might be 6 inches thick, and you have to literally flip over the pages, find the one with logic, and then on that printout, it would have exactly the same thing. You would find that and then go to another book beside it, and it would have a printout of what an index of what all those were. So you literally would read 2 sheets of paper going, okay, so that's my output. It says my system started, that's my terminal bit, etc. It was very time consuming, and it really, not only was it time consuming, the big thing was you were focused more on trying to decodify it, but you lost track of the logic you were trying to solve and get back to the running. So fortunately, we don't have that issue anymore because we have these more sophisticated internal automatic addresses. So an address is the identification of a logic location that is physically connected to a real-world input or output, whereas a variable is an internal address. So this I can say, and I can go and find that particular digital input screw terminal. Okay, so that's digital input 3, and if this was the actual PLC above it, there would be literally the terminal screw with the wire attached to it. And I would say, okay, there it is. I can trace the wire to the actual device. Okay, so let's move on, and we're going to program a timer. So I don't need a lot of this stuff. I'm going to just go and hit delete, delete, and delete. I'm even going to delete my output. And just a single input, which I'm going to say that when my system bit is running, system bits 0 when that's true, I want to start a timer. So let's go to our timers and counters. So there's the menu I get to choose from. If it starts with a C, then it's probably a counter. It starts with, has a T in it, and it's probably a timer. Now we have an RTO, which is an attentive delay timer on. We have a off or a off delay timer. And we have an on delay timer, a timer on delay. And then we have a timer on delay and off delay combined. And finally we have a timer that does a pulse. So we're going to start with the most familiar timer that electricians work with, and that's an on delay timer, or time on delay. I'm just going to click on that, drag it down, and I get this little instruction box. Now each point on this instruction box is actually a physical bit or location, or it's looking for more information. Anytime you have a box sticking beside an instruction, it's asking for more information. In the case of a timer, the information you're going to provide must be of a particular data type. So what I'm going to do is I'm going to right click on this and I'm going to go show the instruction box. No, I don't want to do that. Let's go here. I want variable selected. Now, right now it says, well, hang on a second here. You've asked for this. And right now it is saying, what do you want me to do? Where does it come from? I have to create it. So I'm going to go up to here where it says scope. And what the scope is, in our variable selector, it allows me to jump from my global variables to my local variables. So let's see what happens when I do that. CC Lab number 1, yeah, that's my project, yeah, okay. And now I can give this a name. I don't want a time type. I want to see what's already in there. So I'm going to close this filter. And there's my timer, TO1_1, which is the same as I have here. That's great. That's exactly what I want. Okay, good. So I'm going to give it an alias because TON_1 is not exactly exciting and I don't know what it does. So I'm going to say my first timer. Okay. It's a momentous moment for me, so I'm going to capitalize it. There it is. I have my first timer. And again, I've got that little arrow beside here. So I want to click on that. See what that populates. Okay. Okay, so within that timer, you'll discover that there's actually a collection of information. And again, we have that little period, that delineator between our first part, which in this case TO1_1, that's its official name, and a bool called in, another bool will jump down called q. There's another one that says reg. Now I have to figure out what that is, and it's a bool. The rest of them have this data type called time. So PT and ET and pdate all have this data type called time. Now I'm going to move over and let's take a look at our instruction. So the IN we have here, TON_IN, it shows up on the left-hand side of our instruction box. That IN you see there is telling you that is like a contact on a physical timer that you would energize and start the timer. So if you ever worked with old mechanical timers, electrical timers, you run a wire and you catch it, that would power the timer up. So when the conditions are right, you have the timer running all the time, that input power will be on. So in this case, we're conditioning it so the timer doesn't run 24/7. We just literally have an input. And that is whatever logic that's true ahead of it must be true. So that will start the whole process. Then we have this Q on the other side, on the right-hand side, and it's connected directly to our lug. So that Q energizes when the timer has done its job. In the other PLCs, they would have called this the done bit. They would have called this the enable bit, or the enable bool. The input is the enable, you have to have that in order for it to start, and then the output will be turned on. In this case, once the timing has finished, then the output will be turned on and we call the done bit. So those are resolved, but these two information boxes, I clicked on one and I put this thing, my first timer, and I've got this attention triangle. Something's not right here. If I didn't have this box, it would tell me that my information that I've requested is of the wrong data type. So if we look here, we have PT and ET, and in our variable selector we have .pt and .et. So PT is the program time. ET is the elapsed time. So the program time is an amount that we established that we want the timer to count. Once it is enabled, once that .in is true, so the one before that input is true, then it will start to count. And as it's counting, it keeps track. That is put into our ET, our elapsed time data type. So what we're going to do is I'm going to close this for a second. I'm going to hit OK for a moment, and I'm going to fix my mistake. If I want and I know exactly how much time I want that timer to be, I'm going to take the letter T, and then I'm going to put a hashtag. So it's not like they do on the internet where the hashtag will help you to jump to something. This is to delineate that the T is a time data type. Then I simply need to type in the minutes, seconds, hours that I wish. So I'm going to go, okay, I want it to be a 15-second timer. I don't have to write seconds, I just have to put the letter S. And here, I'm going to just delete that because I don't require an actual variable name into the elapsed time because it's just counting it. Now I can examine these later on. I can use the elapsed time in different parts of my logic to perform different functions. For example, I can say in a math statement, watch this timer, and when the timer is reached 5 seconds or more, I want you to do this. Once it reaches 10 seconds or more, I want you to do this. Once it's complete, then this queue is going to be set. So I don't really need to do the complete, but I can actually use different values of the elapsed time in my program later on. So this is basically all I require to make this timer work. I would simply run this logic. Once that bit's set, the system bit 0 is set, my input becomes true, it starts to count, and I have 15 seconds. So, in our next video, I'm going to turn this on, but the first thing I've got to do is set it up so that the actual simulator will work.